After pushing the launch button, the simulation engine will compute the state of the aquifer for each time step. This process is fairly rapid thanks to the underlying simplified mathematical model, which is based on the vertical equilibrium assumption. In our case, the whole simulation process took less than 2 minutes on this desktop computer. After the simulation process is over, the 2 windows that you can see on the screen appears. I will explain each of them in turn. This window on the left is the visualization window. It allows us to visualize the value of various variables in the aquifer for any time step in the simulation. This slider down here is used to select the time step to visualize. It's currently positioned at the last time step, which represents year 3060 after injection started. Let us go back to the time step where injection ends, that is year 60. What we see here are the vertically integrated CO2 saturation values. A saturation value of 1 means that the vertical column is completely filled with CO2, and a saturation value of 0 means that there is no CO2 present. We can see that large plumes of CO2 have formed around each well. The plumes of the 2 southmost wells have merged. We can also look at the pressure in the aquifer. It is here shown in megapascals. The pressure is influenced not only by the injection, but also on the aquifer depth. So this plot is a bit hard to read. Instead, we can choose to visualize just the overpressure, which is the deviation of the pressure from the initial conditions. We can choose overpressure from the drop-down menu. Since we used a partially open boundary, fluids could exit the domain. If we had simulated with completely closed boundaries, overpressure would be much higher. If we move to the end of the simulation, we see that now the overpressure has largely dissipated, thanks to the open part of the boundary. And if we now go back to looking at the CO2 saturation, we see that the plumes have spread much more out, migrated up and westwards, and collected in some large structural traps along the way. Other fields that can be visualized are Sgmax, which represents the largest saturation values reached, H, which represents the local CO2 plume height, plume SAVG, which represents the average CO2 saturation inside the plume. And if we had included dissolution in the simulation, we would also have been able to visualize the dissolved CO2. In the CO2 inventory window on the right, we can view the state of CO2 in the aquifer over time. The x-axis represents time since simulation start, so it runs from 0 to 3060 years. Most of this period represents migration, since injection operations end about here. The y-axis represents the amount of CO2. The colored zones represents the various trapping states that injected CO2 can be in. We can thus see at any given time how much of the CO2 is trapped in structural traps, as residual saturation, still in the migrating plume, or combinations thereof, or exited the simulation domain. For instance, this orange part represents free-flowing CO2. In the beginning of simulation, most of the injected CO2 is in this state, but we see, as time goes by, that this quantity is diminishing. This concludes our brief introduction to the interactive simulation tool in MRST CO2 Lab. We hope that the application itself, as well as its open source code, will give you some idea about the capabilities of MRST CO2 Lab and help you get started using it for your own studies or research. Thank you for your attention.